Hi, thank you. Good morning, guys. So last speaker is Scott. He did mention wastewater treatment plant. And right now we have an ongoing project. So a couple of faculty in our department and several students, and they are trying to collect effluent along the channel from the discharge point of Oran wastewater treatment plant all the way to the lake. I do have a small image from Google Earth. I did mark the sampling point so we can take a look at that at the end. And also back to the comment, one of you at the end asked the phosphorus input from wastewater treatment plants compared to other sources. I don't think the wastewater treatment plant is the worst. We do have even worse sources. So we can talk about during the presentation. Let me know if you have any questions. So I'm from Utah Valley University. I'm a faculty in the Department of Earth Science. I came to Utah 4 years ago. It's very convenient for me to study Utah Lake. So my previous research mainly focusing on coastal wetlands. We know Utah Lake is very shallow. Majority of the Utah Lake really considered as a wetland. So that is my interest. And as you know, UVU is an undergraduate institution. So my research along with my colleagues here, we involve a lot of students. So they are a really major workforce in all projects we conduct. They are not only doing the field work, they're not only doing lab work, they are participating in all components of research. So right now we have some students working on GIS component to try to put our data on the map, try to visualize and also do some modeling to show how anthropogenic activities affect Utah Lake water quality. So those are the funding agencies. We have funding from IUTAH, very great support, and we have the internal fundings from UVU as well. And we have research students and then the collaborators and UVU here in our university. So basically, I'm going to give you a little background information and then introduce you to out of several projects we're doing. So I'm going to show you some very specific data on biogeochemistry and trace metal analysis. So the first one was going to be on the Transect. It's in the mouth of Utah Lake. So pretty much we're looking at the outlet area. We had 3 transects. One is near the mouth of Utah Lake, and then the other 2 is further down along Jordan River. So the second transect is about 1 mile away from the first. I'm going to show you on the map in just a second. And then the second one will be focusing on the spatial and temporal variations of nutrient and trace metal loading to Utah Lake. I don't have time to show you all the data. We are collecting numerous data, not only stable isotope information and also all trace metals. Today I'm only talking about the arsenic due to the time constraint. And we also have nutrient information as well. We have all the data available, and also we did submit our data to Department of Water Quality as well. Okay, so the Utah Lake general information is one of the 3 major remnants of Lake Bonneville. It's very shallow. So whenever you have some wind, the people will be concerned the safety when they are on the lake. And also it's pretty big. It's one of the largest freshwater lakes west of Mississippi. So it's very important. I always tell my students, I cannot imagine if we don't have the lake in the valley. It's going to make a very big difference. And it's a very important resource, even though a lot of people dislike it right now due to the pollution problems. But we are the ones who did the act. So we have to be responsible to try to find different ways to clean up Utah Lake. So this is just following up with the Scott's presentation. He did mention before the pioneer settlement, the lake might be very different from today. I don't know for sure, but based on the early leader of LDS movement, Parley Pratt's observation, he did mention, okay, Utah Lake was once deeper and cleaner than now. So it was very different image in our mind, right? My research cannot provide all the information to reconstruct what was before the settlement, but we have some clues. So why Utah Lake? This is very important resource, as mentioned to you guys, and also we have to emphasize the anthropogenic activities going on right now, even though we are aware of the impact. But this is Linden Beach, close to the Linden Marina. So my husband and my son, they are going to the lake to collect water samples. So by the way, my husband is also faculty at UVU. He is doing research also on Utah Lake. He is using oxygen and hydrogen stable isotopes and try to build the water budget for Utah Lake. So then he is just one sampling spot in his research. So do you guys know what is this here? It's kind of hard to see since it's kind of I'm low on the horizon.
A sunken boat or a log?
It's a mattress. Oh. And sometimes we go there bi-weekly during the sampling process. This is not the only one we saw. We saw couch on the beach. Then it's kind of surprising, right? But it's happening, still happening, even though we know, okay, we really need the lake for different purposes. So irrigation, water resource, recreation activities, but a lot of people, they are not doing the right thing, right? So we have a lot of room to improve.
That's why I take my naps.
So there are a list of anthropogenic activities. So as you can see, we know most of them, but I want to emphasize here on my maps. Later on, I'm going to show you the mining locations, and we are going to take a look the irrigation lands. So where the lands are around the lake, and also the wastewater treatment plants. We have 7 wastewater treatment plants around the lake. So the one we are working on is an Orem wastewater treatment plant. It's discharging 8 million gallons effluent to Utah Lake every single day. And the Orem wastewater treatment plant is not the largest one, it's Timpanogos. So you can imagine how much effluent we are discharging to the lake daily. And also, Scott mentioned the population growth in the valley. We're going to discharge more and more effluent to the lake. So then there is another focus in our ongoing research. And also, we don't really have a strict phosphorus standard. So the wastewater treatment plants, they are just monitoring the concentration. There are no standard to follow, basically. They told us it might change in the near future, hopefully soon. So this is about the first project. So this is is at the transition zone between Utah Lake and the Jordan River. This is one out of 3 transects. So this is at the mouth. We have 2 more along Jordan River, but I have only time to show you this one today only, since I do have trace metal information. I have carbon and the nitrogen stable isotope information as well. So the purpose of this particular project, we were trying to see the changes of carbon-nitrogen isotopic composition and then carbon-nitrogen ratio pre and post-settlement history. The ultimate purpose, we try to figure out where in the settlement core the settlement occurred. It was a pretty difficult task. We did have latitude dating on the other two transects, but we don't have the date on this one. Then it's unfortunate, but we do have trace metal and stable isotope information. At the same time, we did the carbon-14 dating. It wasn't very successful. We used the shell fragments. We know the shells move everywhere, so it's kind of hard to say, okay, this is the place where the shell deposited. So the data wasn't very reliable based on what we knew. So this is the coring in Jordan River. So we did 3 transects, 3 cores per transect. And the deepest core we got was about 98 centimeters. So this core we were using could drill down 1 meter, but a lot of times we don't get the whole meter long core. So this is how we extract the core out of the core. So it's very, our technician designed this platform was very effective. This is the sampling on the lake. We did sample plants as well. Then there is another ongoing project. We want to see the role of phragmites, even though it's invasive. But at the same time, we could, if we can, maybe we can utilize phragmites to improve water quality as well. So just give you a little background information on delta notation. Whenever we talk about the stable isotopes, we are using this delta notation. So basically, we are looking at a ratio, the rare stable isotope over the most abundant stable isotope. In this case, we're talking about carbon-13 over carbon-12. So we use the ratio in the sample, compare it with the standard. In this case, for carbon, the standard is PDB. It's a formation found in South Carolina, where I got my PhD degree. So we express the data in per mil, which means per thousand, just for practical reason. Since this number is going to be very, very small, it's not practical to use a very small number. That is why we time 1,000 and divide by 1,000 as well. So then it's per mil. So one of our purposes is to trace the organic matter sources. Right now, we have limitations in our method because we're looking at the bulk organic matter. So basically, we can say, okay, roughly we know the organic matter is from C3 or C4 or from anthropogenic products. So we are able to give you the big categories, but it's really hard to quantify exactly how much organic matter from each source. You can see C3 and C4, they are using different photosynthetic pathways. So you are looking at different carbon isotopic composition. So even though for C3 plants, you are looking at the range, the average of carbon isotopic composition for C3 is about minus 26.5 per mil. And for C4 is about minus 12.5 per mil. So based on the difference in isotopic composition, it's possible for us to distinguish different sources of organic matter. So this is for nitrogen. So in my research, I use both plus carbon-nitrogen ratio to have a better constraint on the sources we're looking at. So mainly, I want you to take a look at the fertilizer nitrogen composition. So the nitrogen composition is against the atmospheric nitrogen. So that is the standard for nitrogen stable isotope. And then for the effluent, and then for the manure, you are looking at very enriched nitrogen stable isotope composition. And another very useful proxy is carbon-nitrogen ratio. Sometimes it's kind of hard only using carbon and the nitrogen stable isotope, and the ratio can give us extra information. So for example, if we have algal, we have effluent, we have manure in the lake, how do we know it's from natural vegetation or from anthropogenic activities? So using carbon nitrogen isotope compositions plus carbon nitrogen ratio all combined can give us some useful information. So for the trees, for the terrestrial plants, you're looking at a high carbon nitrogen ratio. Then it means you have less nitrogen in the tissue. That is why you are looking at a large ratio. But for the algal and for the effluent, it's very rich in terms of nutrient, right? Then that means you have higher nitrogen concentration. That is why you're looking at a smaller ratio for those sources. I built a model, but it's really simple, very generalized model for Utah Lake because we know there are so many things going on, right? So it's not easy to capture everything. And also you can see a lot of times you are looking at a range. That is why I said there are limitations on the proxies we're using, but at least we have some useful information, and then later on we can combine with other proxies. So terrestrial C3 signature, which means the trees, the vegetation on land, going to be a major source of organic matter in the lake. And also I did analyze Phragmites, both species. So Phragmites australis and americanus. So one is invasive, the other one considered native, right? The americanus is native, and australis is invasive. So it's showing the very similar carbon isotopic composition. So later on, I'm going to show you the depth profile of carbon isotopic composition. You can see all the organic matter in the lake reflecting C3 signature in general, but we do see some variations. So the benthic algae showing a range, but it's less depleted. Yeah.
Phragmites on Utah Lake, is it native or invasive?
We have both, but a lot of times you see the very, very tall ones, very aggressive ones, then is the invasive species. And also they are very different in the internal structure. When you break the stem, so the invasive one is very hollow. So they are able to let air going through, deliver some oxygen to the root system. Then is one of the reasons why it's so successful, can take over the habitat very quickly. Okay, so this is the Transect. Again, just to remind you where we are. So we have the names for each site. So Utah Lake 1A, Utah Lake 1B, and 1C. I think I don't really have much time to go over in detail, but you can see we have a C3 signature here, but you have an enrichment in nitrogen stable isotope composition, and then carbon nitrogen ratio gave us some story toward the top, especially in this particular site, Utah Lake 1C. So you can see here this star is 1C is smaller than 10. The ratio is smaller than 10, which is an indication maybe there are some effluent and algae organic matter input to the lake. This site is not too far from Timpanogos wastewater treatment plant. So I do want to show you guys the other project regarding the utilization of GIS. Since I don't have much time, I'm just going through pretty quickly. This is the second project I wanted to talk about. We had the sampling size in the lake, and we have the sampling size on the river, and we have the depth profile, which means the deepest part of the lake. So this is close to Bird Island. Let me show you some maps here. So you can see we have 7 wastewater treatment plant, and also we have the mining sites. This is only in Utah County, not including the other counties. We have a lot more mining locations. And then we have the irrigated land. This is only the irrigated land. So I highlighted here. So you can see there are so many different things going on around the lake. So this is the trace metal. Again, I'm referring to arsenic. So basically, you can see the concentration, the outer circles, they are the samples from the river, and then the ones on the lake is not very obvious from this projector. But you can see those data from March 2015, and this is from June, this is from November. So you do see the spatial and temporal variations in terms of arsenic concentration. And then the last map I want to show you, we want to build a model to calculate the lake volume. So we utilized the SRE, the Utah Lake bathymetry contour, and we utilized the LiDAR data we have along Wasatch Front. So basically, this dark gray area showing you the volume, the extent of water in Utah Lake right now. Since this lake level is 2 days ago, I did this for Monday. So this is the volume. So basically, this is just showing you, it's kind of like a column. So 5 by 5, the pixel size is 5 by 5 resolution. So you are looking at the deepest part in the lake, close to Bird Island. So if you use this number divided by 25, you get a depth. So ultimately, we do want to make a model to model how much water coming in, how much water in the lake, how much water coming out for trace metal, for nutrient, and for water budget. Thank you so much. I'm talking too much, just like what I do in classes, I guess. Any questions? I don't really have much time, but I don't know if we can talk later after the other presentation.
Real quick, whether the presentation will be available through the symposium or get a copy, or?
Yeah, I can give you a copy. We haven't, right now we have the drafts of the manuscripts, but if you are using it for yourself, for your information, it's fine. I can give you a copy. Yeah.
You went so fast over the depth slide. It seemed to me like there was about, what, 15 to 20 centimeters of silt from the anthropogenic transition?
Yeah, we did try to locate the depth where the settlement occurred, roughly 60 centimeters deep.
60 centimeters of recent silt.
It's different depending on where you are. Sometimes you are seeing kind of sandy sediments. A lot of times you are seeing clayish, very dark colored organic matter.
But there has been a lot of erosional deposition of sediment on that lake.
Yeah, so you are but still in the lake is relatively slower than the deposition, the sedimentation rate on the rivers. So by our estimate, it's about 3.5 millimeters per year based on our data. Sorry, I'm over time. Thank you.